Hello, how's it going? I think I am streaming. This is for Math 122. If you're one of my Math 142 students, this is not for you yet. I'll be streaming to you guys later today and a bunch of days. For Math 122, if you're watching this live, maybe send me a text. I don't think you would be yet. But, yeah, let's see if this works. Last time we talked, I talked about section 2.1. I want to start in on 2.2. And, I guess before we do that, here's a little thing we should have said last time. Or here's an example I should have done last time. Let me grab some graph paper. So we said that the derivative does a lot of different things for you. One of those things that it does is it tells you the slope of the tangent line. And we use that to find the equation of a tangent line to a graph where we had the equation. But we didn't use the other reason that that is useful, which is if you hand me a graph of a function, thinking about the derivative as the slope of the tangent line is the most straightforward way for me to try to approximate that derivative. Let's go. So here's a function. Let's call this g of x, I guess. And let's say they told us to approximate g prime of 9. Let's go 2, 4, 6, 8, 10, 12, and just to make life difficult, let's use different units on the y-axis. The x-axis is counted by 2s, and the y-axis is going to count by hundreds. And they're telling us to approximate g prime of 9. We want to know what is the derivative at 9. The main thing we were doing at the start of class last time was to say that g prime of 9 is about g of 9.01 or something minus g of 9 divided by 9.01 minus 9. That's not going to work for us. Like, this graph is not good enough to try and look up what g prime of 9.01 is, and it's certainly not going to work in any useful way. Oh, dang. The thing we need to do instead is think about what's the slope of the tangent line. Slope of the tangent at x equals 9. We know that that means the derivative. 9, I sort of happened to choose a special point where, now the thing I want to do, this is hard to demonstrate via live screen where you can't see what I'm doing with my stylus, but I want to try and draw a line that just barely grazes the curve. The frustrating thing about this is I'm not on paper, so my stylus doesn't touch the screen where the thing was. But it looks like if I tried to draw the line that only just barely grazed the curve, it would be horizontal. The slope of a horizontal line is 0. Looks like g prime of 9, if not exactly 0, is about 0. Let's try a different example where there's more to it. How about what's g prime of 4 looks good? What's g prime of 4? I can't do the difference quotient. I go out to 4. I try and hold my ruler up so that that one point is visible, but the rest of the curve is covered up. Or I tilt my ruler so it's going the exact same direction that the curve is, or something like that. If I'm doing this right, this tangent line is just barely going to graze the curve. Mine, if I'm trying to draw it so it touches the curve at this point, and I'm failing because the place where the stylus touched the screen is not quite where the fake ink comes out here. But I get a line that looks like this. This is the right slope, even if it's a little bit too high. I guess this happens with a pencil and a ruler too. I want to figure out what's the slope of that line. How do I find a slope of a line? It's the difference of the y's over the difference of the x's. I grab 2 points. It's good to grab 2 points that are kind of far apart to minimize the errors that you get when estimating these things. This point is 8, we're about halfway between 400 and 500, so I'll call that 450. Come on. Ugh, this stylus is really sucking today. 8, 450. And this point is 0, what is this, 600, 700, 800. We're most of the way to 800. These boxes are cut off at it looks like 860. So the slope is 860 minus 450 divided by the x that goes with 860 is 0 minus the x that goes with 450 is 8. These have a difference of 410 divided by 8 makes like 51 something. I could use a calculator and get digits, but this is all an estimate anyway. I'm getting that g prime of 4 is about 50. I could say the 51, but I don't really think these dots I picked were super accurate. I'm like, there's some room for error when I'm drawing this line. If this was on a test, an answer of, oh wait, the bigger deal is that it was a -8 on bottom, so this is -50. And it should be negative because, hey look, the graph is decreasing at this point. When the function is decreasing, the tangent line will be decreasing and will have a negative slope. So the derivative will be positive when a function's increasing, negative when it's decreasing, similar stuff. Here the slope was 0 at the spot where the graph was completely flat. So the moral of the story is, if you hand me a graph and ask about derivatives, I'm picturing the tangent line, or if I have a ruler, I'm drawing the tangent line and trying to estimate the slope of that line. That's from 2.1. Let's get into 2.2. The key concept for 2.2 is this, that the derivative of a function is also a function. This is maybe not clear. When we've talked about the derivative, we've talked about it at a specific point. But as the derivative, f prime is a thing we can work out for lots of different x naughts. So that's what a function is. It's a way, given a number, to find a number that goes with it. For example, if I had an equation, let's go with g of x equals, okay, let's do x squared. Stick with our first baby example. Then g prime is also a function because I can work it out at lots of different points. I'll work out what is the derivative at -2, -1, 0, 1, 2, 3. We'll go on to 3. If I wanted to estimate g prime of 2, g prime of -2, I pick a number very close to -2. Let's go with -2.001 minus g of -2 divided by -2.001 minus -2. The bottom I can do in my head is -0.001. The top I need a calculator for. What am I going to plug into my calculator? I want g of this number minus g of that number. How do I find g of a number? Well, here's my formula for g. So that means this number squared minus this number squared. This is that weird plugging both directions thing. I need to ask my calculator, hey calculator, what is -2.001 I forgot the parentheses. Parentheses. The parentheses matter, because if I don't put the parentheses, it won't include the negative. Negative 2.001 squared minus, what's negative 2 squared? I can do that one, it's 4. Divide that by negative 0.001. I get a number so close to negative 4 that it's reasonable to make the guess that the derivative at this point is negative 4. Let's try g prime of negative 1. It's about g of negative 1.001 minus g of negative 1 divided by negative 1.001 minus negative 1. On top we have, dear calculator, what is negative 1.001 squared minus negative 1 squared I know is 1. Now divide by negative 0.001. I get a number so close to negative 2 that I would guess the answer is negative 2. I can do 0. What's g prime of 0? I want a number very close to 0. 0.001 minus g of 0 itself. Divide that by 0.001 minus 0. That's 0.001 squared minus 0 over 0.001 minus 0. Those minus zeros aren't doing anything. A number squared divided by itself cancels, leaves one copy of the number. I get 0.001, a number which is very, very close to 0. When the answer is 0, it can be weird to identify that this is a number close to 0, but this is just as close to 0 as our negative 4.001 was close to negative 4. So it's the same kind of deal. G prime of 1, I follow the same thing, and I'm going to end up with a number very close to 2. I'm going to end up with a number very close to 4. I'm going to end up with a number very close to 6. Just like any old function, the derivative is a rule for plugging numbers in. Maybe rule is less of a correct word for derivative because we don't have a formula that gives the number itself, we just get approximations. But the number exists, whatever it is. And that's what a function is. And sometimes, and this situation is one of them, you can figure out a formula for what is that function. And the homework is going to give you some examples like this, where they sort of lead you by the nose in getting enough points to figure out a formula for it. This one follows a really simple pattern. We're adding 2 at every step. That makes it linear. It's got an intercept of 0. It turns out g prime of x is 2x. If I look at this formula, it's working. Double negative 1 is negative 2. Double 2 is 4. Double 3 is 6. If I wasn't convinced it was working, so far we've only checked that this formula works for whole numbers. There's lots of examples you can give of things that are true about whole numbers that aren't true for other numbers. If I was suspicious that this formula was only working by coincidence, I might make my stomach feel better about that by trying what's g prime of some number that's not a whole number. Let's try 8.431. That should be take a number very close to 8.431. I'll take 8.43101 minus g of 8.431 itself. Divide that by 8.43101 minus 8.431. How do I work out those g ofs? That's that number squared minus that number squared. Divided by, what do I get when I subtract those? 0.00001. So now I pull out my calculator and say, hey calculator, what is 8.43101 squared minus 8.431 squared? And now divide that by 0.00001. I'm getting 16.86201. I don't think this is what the derivative is, but I think it's pretty close to the derivative. I thought that g prime of x might be 2x. If I double 8.431, I get 16.862. This is, sure enough, a number that is very close to 16.862. Did I write the number down wrong? Yep, it was 862, not 26. So yeah, it sure looks like this is a number very close to that number, and maybe if I put in some more zeros it'll get even closer, and yeah, I can come up with a formula and convince myself that my formula works. Sometimes. You've taken an algebra class, so you're probably pretty good at, if your formula happens to be linear, you can write down a formula, or a few other patterns are noticeable. In general, it's hard to look at a chart full of numbers, though, and come up with what is the formula that makes this chart, makes this pattern happen. And we'll do a bunch more of that. But the key thing is, the formula maybe exists. And if the formula doesn't exist, the chart full of numbers certainly does, and that's enough for a thing to count as a function. We can do the same thing with a line. Can I make some more graph paper? Let's try sketching the graph of a derivative given it's the graph of a function. So let me draw a curve. I'm going to draw it in purple, something like... ooh. And let's make our graph just start at this point and go on forever on the right. So this closed circle is saying no more graph to the left of this point. The arrow is saying that the graph continues forever to the right of this. And let's add some tick marks. 0, -1, -2, -3. Let's make this 2, 4, 6, 8, -2, -4. Okay, we got a graph. At every one of these points, there's supposed to be a derivative. How do I find these derivatives? I can estimate some of them by thinking about tangent lines. I draw a tangent line. That went bad. I'm trying to use a piece of paper as a ruler, and it's too thin, so my stylus is slipping on top of it. I got a line something like that. About what is the slope of this line? If I grab two fairly far away dots, I should name this function. Let's call that y equals h of x. Now I'm going to sketch y equals h prime of x. I don't need to use the same scale, although it would make sense to on the x-axis. The thing I'm trying to estimate with that tangent line is h prime of -3. I'm out at x equals -3 when I drew the tangent line. So the thing I'm about to learn is where should I put this dot for the derivative? What is my slope here? I went from -2 to +8. That's about 10. I know it's not quite 10, but this is just an estimate. We went up 10 over 3. It's about 3 point something. 1, 2, 3. I'll draw something up here at 3 point something. I got a dot around here. I can ask what's h prime of -2. I'm going to erase this line and try the next one. Ooh, that's the rotten thing about these bad tangents. Ooh, here's my clipboard. That's a much better tangent line drawer. I'll draw this line right here. Something like this. The tangent line is... I went through the curve, but I have the right angle. Here's a point. And here's a point. Our slope is still positive. Now we're only going up 8 or 9-ish, up 9 over 4. It's about 2 point... That's 2 1/4, right? So now we're at 2 something. I guess I need to label these tick marks if I'm actually using them. I can ask what's h prime at -1. I draw a line here. I try and sketch a line that is at the same angle. Oop. Dang it. I can do better than that. Let's make the thing like this. Hey, cool. That's the goal. You want a curve that just barely grazes the line, that's going the exact same right direction. So I approach the curve, I just kiss it at that point. Kissing is a I guess it's originally a thing they say in pool when two pool balls are just touching. They call that kissing. Here is a line that is kissing the curve. They are just barely glancing each other. What's the slope of this line? I grab a dot, I grab a dot, I think about a rise and a run. This is going up 1 to about 3, and it's going over 7. So h prime of -1 is about up 3 over 7. That's about a half. H prime of -1 is about a half. Cool. What's going on at 0? 0 looks like the place where the graph is horizontal. I don't need to think about rises and runs. A horizontal line has a slope of 0. What's going on at 1? I got a slope of about... I'm going to stop trying to use a ruler now. I got a slope of about... Now it's decreasing. From here to here, our rise is we went down 6 over... 4 something. So down 6 over 4 something is -1.5. I'll put a dot about -1.5, and so on and so on. Our next one is going to be much steeper. This is one's got a slope of about, ooh geez, from here to here we went down 2, 4, 6, 8, 10, 12, 14, and over 3. So that's 4 something, like real low, but that looks like the steepest it's ever gonna get. Now it's gonna be flatter at this point. Looks like down 6 over 2.5. That's around, I don't know, 6 over 2.5. Two something. And then at 4 it looks like it's even again. And then at 5 it's going up again. So this is a rise of 2, 4, 5 over 1, 2, 3, 4. Down 5 over 4 is 1 point something. Oh, that's not what I was going for. I wasn't here. Oh man. I lost all that stuff. Anyway, you get a bunch of dots. And you can say, hey, probably if I took these derivatives at these in-between points, it would probably connect these dots in something like that way. I get something like that. But, and now here's the even trickier thing, I don't need to be that advanced to be actually doing a computation. There's going to be versions of this problem in the homework where we do the same thing, but we don't even put units on the y-axis. Here's y equals h of x looks like this. What's y equal h prime of x look like? Let's make this one a little bit complicated even. Let's have a graph that starts existing, goes up with a crazy vertical asymptote, comes back from that crazy vertical asymptote, and then goes up like that. What's the derivative of this look like? There's no scale on the y-axis. I can't try to do computations on the derivative. Actually, I should put a scale. Well, as long as the scale on the x-axis here matches the scale on the y-axis here. I don't know what else to say, but let's put 1, -2, 2, 4, 6, -2, 2, 4, 6. There we go. First off, the function doesn't exist left of -1. If there's no function, there's no tangent line to ask about, so the derivative also can't exist left of -1. So the fact that this is empty tells me the matching part over here is also empty. At the start, my graph is increasing, so I have some positive value. I ask about the next value and the next value and the next value, and I see that the graph is getting steeper, right? So this one is increasing at some steepness. I don't know what steepness level that is. I put it at this, but it could be higher or lower. I don't have anything on the y-axis, so I don't know how much higher or lower high and low are. But I know that the next one is even steeper, and then even steeper, and then even steeper. So whatever these dots are, they're going to be getting bigger and bigger. And in fact, as we approach that vertical asymptote, as that thing is approaching it, it's getting really, really, really steep. The steepness is going up to infinity. So the derivative, it turns out, is also going to be having a vertical asymptote. Not because the function is big, but because it is steep. I've got a very steeply increasing function going on right here, so I need to put a very big positive number. It's going to get even bigger, so this is going to get even bigger. So yeah, a vertical asymptote in the function became a vertical asymptote in the derivative. When I ask what's happening at 1, there is no function at 1. So again, there is no derivative. I don't try and add a dot here. What's happening a little bit to the right of 1? So I look at this point and say, now we're decreasing very steeply. So this is going to be a very big negative number. How big? I don't know. Pretty big. And the next one is also negative, but not as steep, not as steep, not as steep. So I'm getting a negative number that is smaller, a negative number that is smaller, a negative number that is smaller. The key thing I need you to be focusing on is that here I am looking at the steepness, and that is telling me here where to put the dot, high or low. This is a pretty steep, downwardly slanted angle, so I put a pretty big negative number. How big? How big I don't know, because I don't have any values, but not as big as this, even bigger than that. This point is worth remarking on. When I'm trying to think about derivatives, the places where the derivative equals 0 are usually the most clearly visible. So that's the spot that I can see most clearly. This spot is the spot where the derivative equals 0 is 4.6 exactly-ish. So the derivative equals 0 at negative 4.6. If I sketch these dots connected, I'll get something like that. What's happening after 4.6? Now we're increasing a little bit, increasing more, So I get a small positive number, bigger, bigger, bigger. Small positive, bigger positive, bigger positive. Something like this. The derivative should look something like this. This type of problem is a nice one to put on an exam because it asks you to really understand what some of this stuff is. It's even better to put as like a matching problem or something where, hey, look at these which of these things might be the derivative. What are the key features here? The function was increasing and increasing steeper and steeper. So I'm getting positive numbers that are getting bigger and bigger. Now it's decreasing and then increasing, so my derivative is negative and then positive. The exact spot where the thing equaled 0 is the most uniquely identifying trait of the derivative, I guess. If I had 5 graphs that might be the derivative, I would be looking at that as my my clearest way to say this is the right answer and that one is not, because this particular spot is very specific. Yeah. Things to note. We said this out loud earlier, but I should get it written down somewhere. Note, f prime of x is positive when f of x, the original, is increasing. The word when here means I'm talking about the x-axis. This function was decreasing between 0 and 5. The derivative wound up being negative between 0 and 5. That chunk of the x-axis that lines up with the original function decreasing is the chunk of the x-axis for which the derivative is negative. F prime is negative when f of x is decreasing. And f prime of x is 0 when f of x is horizontal. The class is going to have a lot of these three-part statements where when you're on this side of the line, this happens, and when you're on that side of the line, this happens. And the third one is always the baby bear, where the thing is just right, you're on the border between the other thing happening. I like thinking of these as Goldilockses or something. Yeah, let's do a matching example. Do I have pictures of this? Am I thinking of the wrong section? Yeah, let's do a real quick picture one. Looks like these are a lot less fun when I don't have a classroom in front of me to answer them. Example. Here's some functions. For each, their derivative appears also. Is one of these functions. Which is it? So I'm going to sketch 8 functions real quick. I want to try and mix them up. Let's draw them all in red. Here's a function. 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 And here's a function. I forgot to draw a square around that one. Let's give these names. A, B, C, D, E, F, G, H. And the thing I'm telling you is that for each of these 8 functions, its derivative is one of these things in the graph. I'm drawing these by hand, so, not that exactly. But here's a function. What's its derivative? Pause the video. Try and figure this out. There's not too much going on here. I'll do the first one right now. Or, I guess maybe you paused it, and I'm doing it much later. A is a function. Is that increasing or decreasing? Well, it's neither just increasing nor just decreasing. It's decreasing for a while, and then it increases after that. The place where it switches is very specifically at x equals 0. I'm assuming that's what that y-axis is there for. Is one of these functions. So if the original is decreasing, then increasing, the derivative should be negative, then positive. Are any of these functions negative, then positive? This one is positive, then negative, then positive. This one's always positive. This one's always 0. This one's negative, then positive. That sounds right, except this one switched places over here to the right of 0. And ours switches places exactly on 0. Which one is this? That's this one. Is negative, then positive, switching places right at 0. So that's H, is the derivative of A. What's going on with B? B is a function that decreases, then increases. Where does it switch? Somewhere here. We're decreasing, and then we're increasing. And we switch somewhere to the right of the x-axis at some positive number. Well, we notice this guy does that. He's negative, and then positive. This guy was decreasing, then increasing, and this guy is negative and then positive. So yeah, that'll be it. The derivative of B is E. None of the others have that right. C. C is always increasing. So I want a derivative that's always positive. Not only is it always increasing, I want to be able to, like, now I need some more second level thoughts. This guy is flat and then steep. So our derivative is always positive, small on the left, big on the right. I'm looking for a function that is always positive, but starts out small and ends up big. I'm looking for something that moves from being a small positive number on the left to being a big positive number on the right. And I go through, that doesn't look right, and that doesn't look right. And this one, that doesn't look right, and that's not doing it, and that's not doing it, and that's not doing it. And this is a place where the room full of people gets mad because the answer is C itself is one of these functions that is always increasing, small and flat on the left, steep but still positive on the right. So it is flat and then steep corresponds with the fact that it is small and then big. This thing is its own derivative. That's a thing that can happen. It wasn't expected, but it could. What's going on with D? It isn't increasing or decreasing. It is flat here, and it is flat here, and it is flat here. At all times, it is always flat. So the derivative should be 0, and then 0, and then 0, and then 0. Which of these functions is always 0? That's D. D is always 0. Okay. What's up with E? E is always increasing. Does it get more steeper or less steeper? Whatever steepness it has, it is the same steepness here as it is here, as it is here, as it is here. So it's not going to be big then small, it's not going to be small then big, it's going to be whatever value it is, it's going to stay that steepness the whole way through. So the derivative should be always positive. But it won't have small parts and big parts, it will always be the same height, whatever it is. Well, that's G. G is a positive number all the time, and it is the same positive number all the time. Whatever steepness you're thinking of, it is that steepness constantly. So the derivative of E looks like G. What's up with F? F is decreasing and then increasing, and it switches about here. So I want a derivative that's negative and then positive, switching about here. We saw that already. That's E. But wait, we already used E. That's okay. B and F can both have the same derivative. Multiple functions can have the same derivative. That's a thing that's going to happen sometimes. What's up with G? G, just like D, is always flat. So the slope should be 0, and then 0, and then 0. Which of these functions always has a height of 0? That's D. What's up with H? It's always increasing, so the derivative should be always positive. A bunch of these functions are always positive, so I want to think more deeply about this. It is steep, then flattest in the middle, not completely flat, but flatter, and then it goes steep again. So what does that tell me about the slopes? The slopes are always positive, we said, but the slopes will be big, then small, then big, but always positive. Which of these does that? A does that. It's always positive, but it goes big, small, big. So that's A. I'm making notes on this page, and I'm not doing a great job of keeping track of when am I talking about the original function and when am I talking about the derivative, and that's the tricky thing going on here, is I'm looking at these functions sometimes as the original function and sometimes as the derivative, and it's hard to do, but we can do it. Cool. So I think that's it for 1.2. And I'm going to keep on moving. I should check and see if I'm still streaming. Hey stream, am I streaming? It says I'm live. Cool. Oh, hey, I can look at the video on my phone and see if my phone shows me as streaming this stream. I guess if you're watching this video later, I will erase these when I start talking again. Yep, I looked at me. I'm on the YouTubes. Look, Mom, I'm on the YouTubes. Cool. Let's get into 1.3, which is mostly a notation section. It talks some more about applications. And we start talking about the second derivative. Hang on 1 second. Trying to be really conscious of not sniffing or coughing into the microphone, and it's rough. Okay, so a thing about calculus. Calculus is one of many things that was invented in two places at the same time. In England, it was discovered / invented by Isaac Newton. And in Germany, it was invented / discovered by Wilhelm Leibniz. And who did what first, people get into arguments about. I guess the real question is which of the key observations is the thing that counts as calculus, and some of them this guy did first, and some of them that guy did first. The thing we care about at the moment is that they used different notation, and we're kind of stuck using both notations. Newton used the notation that we've been using so far. You would talk about y as a function of x. The derivative would be y prime is f prime of x. We haven't talked about y prime, but the prime means derivative of. We most like talking about this as a function and giving a name to the derivative also as a function. But that's kind of a more recent phenomenon where it turns out in math a lot of ideas are a lot cleaner if you normalize this idea of a function beforehand. Newton wasn't as obsessed with functions. He just used an apostrophe to mean the derivative of something. And now we sometimes put that on the variable, or sometimes we put it on the function. Either place we put it, it means the derivative of. Leibniz didn't do that. When Leibniz had a function, and he wanted to take the derivative of it, he called that dy dx. This is Leibniz notation. For the derivative. And the key thing about it is we write it like it's a fraction. And the reason we write it as a fraction is because it's representing the difference of the y's over the difference of the x's. The d there is for difference of. We subtracted some y's and subtracted some x's, and that's the thing we use to approximate the derivative. So it's kind of giving you some information about the family history of this derivative. But it's not a fraction itself, and in particular, you can't cancel the d's. It sure looks like you should be able to just cancel the d's, but that's not what this is. We write it like a fraction, and sometimes the fact that it looks like a fraction we're going to use as a mnemonic device to remember stuff, but it is not itself a fraction. We write this as, so dy dx, we pronounce dy dx, or we call it the derivative of y with respect to x. In this class, we're only going to talk about functions of one variable at a time. But you can imagine there are situations in engineering and physics and stuff where there's lots of variables floating around. I've got 10 variables here that are functions of those 4 variables over there, where when you want to take the derivative of something, it becomes relevant. Well, which input are you thinking about? If I had a function with an x and a y and a z in it, then there's going to be an x derivative and a y derivative and a z derivative, and having something built into the notation to say I'm taking a derivative, the thing I'm taking the derivative of is y, and the thing that is being the input variable is x, can be useful. Like, it is nice to give more information. Just by writing down dp dt, I automatically know that there is some function p of t out there. Like, the Leibniz notation helps me look at it and understand what's going on out there. Looks like a fraction. It isn't a fraction. We do sometimes... If it was a fraction, I would be allowed to write dp over dt like this, and we do write it like that if you're in a situation where your space is too cramped to fit a tall fraction. You can write it with a slash instead of a fraction bar. Like, we use the same penmanship, I guess, as if it was a fraction. We may say think of it as, sometimes we'll pull the y off of the fraction and write it as d dx y. So the thing that we are doing to y is taking the derivative of it, and this d dx without the variable on top is a useful notation for derivative of. Derivative of. If I was in Newton's form, then the derivative of would be like the apostrophe of f, and you don't really want apostrophe to be the name for something, so that's another good thing about it. Good things about Leibniz notation. Yeah, I've said all this stuff. I'm looking at my notes here. It reminds you of a lot of stuff. Writing this tells me that there is a function out there. It also helps me remember that I have p of 2.001 minus p of 2 divided by 2.001 minus 2 is the thing I do to approximate the derivative. Well, the fraction being written like this helps me remember p's on top, t's on bottom. That could be valuable if I'm trying to remember that. It also helps me remember the units are p units over t units. We mentioned this last time. The units of any derivative are always y units over x units. Well, that fraction is telling me which one's on top and which one's on bottom. These are fairly good things about Leibniz notation. Downsides of Leibniz notation. The big one to me is if I want to say f prime of 3, hey, I just said it. Take the derivative at 3. This dy dx doesn't really have a place to put the 3. Like, it's not a function sticking the parentheses there. I guess we could do that, but we don't. The thing we do to say derivative at 3, we write dy dx, we write this vertical bar, and at the bottom of the vertical bar, we write x equals 3. You don't need to be using a derivative for this vertical bar notation. So this vertical bar, if you're pronouncing it, you might call it at, or evaluate it at. It's kind of the thing that I think this used to be a more common notation that got used less once we had functions. The nice thing about a function is it's got a notation for plugging a number in. You can use this for anything. I can say x squared bar x equals 2, and that means 4. Take x squared, now plug in x equals 2. You can use it for anything. It's most commonly used for dy dx because it's a thing that is not a function. It's sort of the leftover from converting to function notation. Yeah. So, derivative of a function is dy dx. This is not new. I mean, it's new notation, but it's not a new concept. A thing that is new is that y prime is approximately delta y over delta x. This capital Greek delta is used to represent difference of. And what it's trying to represent here is the type of differences that we use when we approximate a derivative. When I say, if I'm approximating f prime of 3 by saying it's about f of 3.01 minus f of 3 divided by 3.01 minus 3, this thing on top will sometimes be given the name delta y, or delta f if I'm not using the letter y on this function. And that thing on bottom will be delta x. So delta y, delta x, when I use this description, is a fraction. It's the name we give, I guess it's two names. It's names we give to the differences we use approximating derivatives. Right? So, how does this get used? One of the ways this will get used is in a problem where someone says g of x is 2 to the x minus x. Approximate g prime of 4 using delta x equals 0.02. When we approximate a derivative, we're picking a number really, really close to 4. And one of the things we'd like to be able to have a conversation about is what number should I pick very, very close to 4? The point of the derivative is as long as the number gets smaller and smaller, you'll get closer and closer. But maybe want to pick one particular approximation and be able to talk about it. Giving a name to delta x is a way to do that. They're telling us to pick our number very close to 4 so that the distance between the new one and the old one is exactly 0.02. What number should I pick so that the new number is 0.02 away from the old number? Well, that should be use 4.02 as your really close number. So g prime of 4 is about g of 4.02 minus g of 4 divided by 4.02 minus 4. This number on bottom is 0.02, which is what it should be because that was delta x. This thing on top is plug in 4.02, plug in 4, subtract. So that's, come on, 2 to the 4.02 minus 4.02. That's g of 4.02 minus g of 4 is 2 to the 4 minus 4. That whole mess on top is going to be what we would call delta y. What do I get when I evaluate those? I need a calculator for that. Hey, wake up. What is 2 to the 4.02 minus 4.02 minus, I need to wrap this in parentheses because it's minus the whole thing, 2 to the 4 minus 4. Actually, I could have done that one in my head. That's 12, I think. Subtract them, you get this. Now divide that by 0.02, and I get 10.167. Okay. This thing that I got is not G prime. This is exactly delta y delta x. I guess exactly is a bad word to use because I've got these dot dot dots. I haven't written down all the digits. And it's about dy dx. The thing we want to keep clear on is that dy dx is the actual derivative. Delta y delta x is not the derivative, it's an approximation of the derivative. Meanwhile, I would say that this 10.1675 is about dy dx. I would say that this 10.1675 is delta y delta x. Note, in this case, if I had a negative delta x, negative 0.01, that'd use g of 3.99 minus g of 4 divided by 3.99 minus 4. You're allowed to have negative delta x's. That tells you pick a number left of the point. That works just like you might guess it does. Let me do an example where I can emphasize the difference between exactly and approximately. Let's take h of x equals x cubed, and let's approximate h prime of 2 using delta x equals negative 0.0001. Well, h prime of 2 is about, to approximate a derivative, I need to pick a number very close to 2, and they've told me what number to pick. They told me pick a number that is left of 2 by 0.0001. What is that? That is 1.9999? Yes. Minus h of 2 divided by 1.999 minus 2. I think I wrote. Yeah, it's the fourth place, so there's 4 nines. That'll be negative 0.0001 on bottom. That's right. That should be a delta x on bottom. The thing on top will be delta y, will be 1.999 cubed minus 2 cubed. I need my calculator for the top. Dear calculator, what is 1.999 cubed? Something very close to 8. When I subtract the 8, I get negative 0.01199. Now I need to take that number and divide it by negative 0.0001. Uh-oh. Oh, I wrote divided by divided instead of negative. Divided by negative 0.0001. Have I screwed this up? What? This is not the answer I'm expecting. What did I type in the first time? Second enter to retype, second enter to retype, second enter to retype, second enter to retype. 1.999 cubed. Oh, there were supposed to be 4 nines. 1.999 cubed. Subtract the 8. Divide by negative 0.0001. Okay, so yeah, I wrote this down wrong. There's supposed to be an extra 9 here. That's where I went wrong. And our answer turns out to be 11.9994. 0001. So, the thing I want to emphasize is how we talk about this. I say delta y over delta x is 11.99940001. That leads me to conclude that dy dx, which is the derivative, the name of the function was h prime of 2, is about 11.9994. Right? Delta y delta x is this, which tells me the derivative should be approximately that. This number is so close to 12, this makes me guess that dy dx is probably exactly 12. Once I know the derivative is exactly 12, I should say that delta y delta x's are probably going to be about 12, and sure enough they are. The thing we're gearing up for is we're going to be headed to a place where we switch what's the approximation and what's the exact value. Like right now, I don't know how to find exact derivatives, so I use these approximations and use these to approximate derivatives. By the end of chapter 3, we're going to be better at finding derivatives than we are at finding approximations. And in that case, this notation is going to be super useful because we'll say, I know this is 12, and that lets me say things about these y values and these x values and such. And that's going to be nice when that happens. Yeah, let's try an example where we just talk about derivatives. Am I running out of time? I just went over an hour. There was a thing here that said it was counting down from an hour, and I'm worried that the stream's going to cut off after an hour or something. I'm going to look at the stream on my phone and see if it's still going. Actually, I'm going to do that, and I'm also going to go get some water. I'll be back to the stream in just a minute or two. Hey, I'm back. It's a me. Andy. How's it going? Let's do an example. C equals C of A is the total cost to build a house whose square footage is A. That's not how you make an A. Square footage is A. Let's ask some questions about this function. What are the units on C and on A? Well, C was a cost. They didn't tell us what the units are, but it would be reasonable to assume that they're probably in dollars in this country. A is the square footage of a house. You measure square footage in square feet. Cool. Got the units on C, got the units on A. 2. What are the units on C prime of A? This is a derivative. Derivatives are always in y units over x units. I can remember that because it's dy dx. The y's are on top. What's our y thing here? Our y thing is C and our x thing is A. So this should be dollars over square feet. That's dollars per square foot. Cool. Cool. 3. If C of 4,000 equals 200,000, what does that mean? Turn that into a sentence about a house. Pause the video, think to yourself for a second. Turn that into a sentence about a house that involves the numbers 4,000 and 200,000. Okay. One of these things, A is 4,000. So a bad version of a sentence would be when A equals 4,000, that's when C equals 100,000. That's not really a sentence about a house yet, though, but that's a start. Adding units helps. 4,000 square feet, $200,000. A house, they're telling me that should be the cost to build that house. A house of 4,000 square feet costs $200,000 to build. Cool, I got a sentence about a house. Like, I understand this sentence. Neat. The derivative one is the hard one. 4. If C prime of 4,000 is 70, write that in Leibniz notation. And interpret. Interpret means write a sentence that says what that means. A sentence about a house, not a sentence about derivatives. Let's start with the Leibniz notation. The Leibniz notation is the dy dx thing, but our letters aren't x and y. It's got to be d something, d something. The y thingy is the c, and the x thingy is the a, so it's going to be dcda equals 70. But I haven't used the number 4,000. The way I interpret that is I got to use this terrible bar. dcda at a equals 4,000 equals 70. This one is more awkward to write. This was one of the downsides of Leibniz notation, is it's a real pain to write sentences about. dcda at a equals 4,000 is 70. Cool. How do I interpret that? It helps a lot to have the units in mind, although that will lead us down the wrong path first. something is $70 per square foot. It'll be tempting to say the house costs $70 per square foot, but that's not right. It costs $200,000. 200,000 divided by 4 is 50, not 70. So this can't be right. The total cost of the house is not $70 per square foot of the house. So what does the derivative tell me if not this? Geez, I should have... I'm having stylus problems again. I should have changed the battery when I took a break a second ago. Cool. What's the derivative telling me if not that? It's telling me about a rate of change. It's saying that at this production level, or at this square footage level, the rate at which the cost is changing is at a rate of $70 per square foot. The cost is changing. This is still not a good sentence. At a rate of $70 per square foot. As A changes. Something like that. That when you change the A value, the C value should change also. How should the C value change? It should change at a rate of about $70 per square foot. So I know that a 4,000 square foot house is going to cost this much. And if you wanted to change that 4,000 a little bit, so I've been talking about building a 4,000 square foot house, and I'm thinking about making a small change, and I'm interested in how is that going to change the price. If you change the square footage, the price will correspondingly change. At a rate of $70 per square foot. Okay, this is something I can make sense out of. So it's not about the total cost of the house, it's about the cost of a small change. That makes sense. When we talked about derivatives, we were always thinking about all these small changes. I unmuted my microphone, didn't I? Yes, I did. Cool. So a good way to think about this is that the thing that costs $70 per square foot isn't the main square feet of the house. This is the cost for additional square feet. From a blueprint, so from a square footage of 4,000, additional square feet on the house will cost about $70 per square foot. And the important thing to keep in mind is this is all in the blueprint stage. This is talking about a hypothetical house to be built. Once you've built the house, adding an extra square foot will probably cost you more than 4,000 because you have to tear down the wall somebody already built or something. This is talking about the planning stages where this is possible. And this is a key thing to get. This is one of the biggest mistakes people make is interpreting a derivative as telling you something about the whole cost of a thing instead of just telling you about additional small changes to the cost. And here's the key thing that we can answer from this. Having written that sentence out, we can now answer a pretty... Here, let me just label this part. So, example. Suppose, same situation, C of 4,000 is 200,000, and C prime of 4,000 is 70. Approximate. C of 4,300 What is C4300 supposed to be telling me? This is the cost to make a 4,300 square foot home. I just said what this fact tells me, that making a 4,000 square foot home costs about 200,000. I don't need calculus to say, well, this is a little bit more than 4,000 square feet, so the total cost should be a little bit more than 200,000. This is like a first level approximation. Is that it should be a little more than 200,000. My first fact tells me making a 4,000 square foot home costs $200,000. If you want to make something a little bigger, it'll probably cost a little more. That's not using calculus, though. We haven't used this second fact. The thing the second fact is telling us gives us a way to say way more specifics about that a little bit more. It tells me how to say how much more. You want 300 extra square feet? Well, this fact about the derivative tells me those extra square feet you're asking for costs $70 a piece. How much more than 200,000 should it cost? I need to add on, well, how many extra square feet did you want? You wanted 70 extra square feet? Those cost you, wait, no, hang on. I screwed that up. It costs you $70 per square foot. How many extra square feet did you want? Well, going from 4,000 to 4,300, you wanted an extra 300 square feet. How much is 70 times 300? It is 7 times 3 is 21 with 3 zeros after it. So I want 200,000 plus 21,000 makes $221,000. That's our estimate for the price of a 4,300 square foot house. I want to zoom in on what we just computed, because we want to be able to do this for lots of derivatives, even when we haven't written out this sentence. Like, this sentence is doing a lot of legwork for us. That's saying the square footage, that additional square feet cost about $70 per square foot. Like, this is what a derivative means. And it's really important to be able to talk about other derivatives to wrap our heads around what we just said. The thing we just said, here's how I like writing it. We just said that the new value is approximately the old value plus the rate of change times the change in x. Right? To say what was going on at C of 4,300, we approximated that by saying, well, I know what C of 4,000 is. I know what C prime of 4,000 is, that's the derivative. I wrote dy dx, but in that case it's dc dA. And that delta x is saying how much did the x's change by? That's what 4,300, that came from 4,300 minus 4,000. Delta x is still allowed to be negative. If we think that additional square feet on the house cost an extra $70 per square feet, it should also work backwards, that if I figure out a way to shave off a few extra square feet, that should save me about $70 per square foot shaved off. If the derivative is the derivative, then it should work on both sides. And yeah, this is a way to use the derivative to approximate nearby values. This is why we like that delta x notation. What else can we do with this? A key thing going on is that dy dx is approximately delta y over delta x. It's kind of the definition of the derivative. It's the thing you can approximate by taking delta y and delta x. So that means that dy dx, which is the derivative, if I multiply both sides of this by delta x, I know that dy dx times delta x is about delta y. That's a way of thinking about what this is saying. Dy dx times delta x gets me about delta y. You want to know what's the new y value? Well, I know the old y value. How much should I change it by? Delta y means the change in y. It is how much should I change the old y by to get the new y. That's another way of looking at what this is telling us. Another way of thinking about this same equation, you've seen the point-slope form of a line before. If you want to write down an equation of a line, you need to know the y value and the slope, x minus the x value. This is basically a version of the same equation. Now it's not about approximating a thing. Like, part of what we're saying is, if I know the value here, and I know the slope here, then I can approximate the value here because it's pretty close to the tangent line. The point of the tangent line is it's really close to the curve, at least if you are near that point. If I was zoomed in, I couldn't tell the difference. This is pretty close where I can tell the difference, but still pretty close. What's the equation of the tangent line? Well, the equation of the tangent line is the y value is take the y value that you know, add the slope, times how much did you change the x by. This is a y value that you know. The slope is a derivative, or the derivative is a slope. And the difference of the x's is a delta x. This is the same setup. It's kind of nice to, like, hey, maybe you had problems remembering the point-slope formula. Well, now you have a thing that integrates that as one of the ways to remember things. Or vice versa. If you didn't have this memorized, hey, it's just another version of this. This concept works for functions where I don't have those sentences worked out. Example. If I tell you that f of 3 is 9.2, and f prime of 3 is 11, approximate f of 3.1. Well, a new y is about the old y plus the derivative times the change in x. The new y, the thing I want is, hey, what's f of 3 point, not f prime, what's f of 3.1? It should be about the old y, the thing I know is f of 3, plus the derivative, that's another thing we know, because they gave it to us. Damn stylus. F of 3 plus f prime of 3, which is another thing they gave us, times the delta x. They didn't spell it out, but we can work it out. You want to know what's happening at 3.1? So the new x value, delta x is new x minus old x. Our new x is 3.1, our old x is 3. You want to wiggle the x value by a small amount, 0.1. Well, the thing the derivative does is it tells you what's the ratio of the x wiggle to the y wiggle. 11 times 0.1 is 1.1. Wiggling the x by 0.1 is going to wiggle the y by 1.1. Your old y was 9.2. Wiggling that x by 0.1 will increase the y by 1.1. When you increase 9.2 by 1.1, you get 10.3. That's our best approximation for f of 3.1. The approximation should be more precise if your delta x is small, which means if you pick a number very, very close to 3, this approximation is probably more and more accurate. Yeah. Yeah, let's talk about the second derivative now. So that's that problem is just an example of using delta x, and the reason we're using it is we want to be able to, it is nice for conversations like this. Like this, using the derivative to approximate nearby values is one of the fundamental things of what the derivative is. It's really close to how, if I wanted to approximate f prime of 3, I would approximate it by taking a number pretty close to 3, subtracting f of 3, dividing that by 3.1 minus 3. The thing we're doing here is just a very mild reworking of the approximation that we used to define the derivative. We're just switching the things places. Multiply both sides by this, add the f of 3 to both sides. It's pretty easy to turn this line into that line. The thing that's not clear is, like, is the approximation better or worse on this or that? And it's it's scaled by a factor of 0.1, one way or the other. But the point of the derivative is this. This is very close to just being the definition of the derivative, but it's said in a different way. Let's talk about the second derivative. We made a big deal about f of x as a function. Then f prime of x is also a function. That was the name of the section 2.2. Well, if f prime of x is also a function, it also has a derivative. What do we give that a name? Well, the thing that indicates derivative of is an apostrophe. So I want to take this function and add an apostrophe to it. Well, that's okay. Now there's two apostrophes. That's the name for the second derivative. This is f prime. This is sometimes read as f double prime. I don't think I've heard people say f prime prime, but I mean, I guess you can. Double prime is more common because once you take the second one, there's a good chance you're going to run on to third and fourth. How do we do this for notation, for Leibniz notation? The thing they do for Leibniz notation seems psychopathic until you think about what they're doing here. This dy dx, you got to think about it as a dx in front of a y. What is it that we did to y to change it to the derivative? We stuck a d and a dx on it. So to write down the second derivative, I want there to be two d's, two d dx's out front. So the way they write that is d squared y over dx squared. Why isn't the bottom d squared? Well, because the bottom dx is all one thing. This is how they write the second derivative here. This is Leibniz notation for the second derivative, and it's weird, but that's how they write it. Computing the second derivative is in general hard. If I have a function, let's take a simple example. Let's take y equals x cubed, and let's say we wanted to approximate y double prime at x equals 2. By the way, the thing I'm about to do is horrible, and the only reason I'm doing it is to illustrate that it's horrible. So if you're taking notes, don't feel obligated to pay too much attention to what's going on here. To approximate this is the derivative of something. I need to take the thing it's a derivative of, y prime, and evaluate that at a number very close to 2, and at 2 itself, subtract and divide. Well, now how would I approximate each of those things is also a derivative? How do I approximate y double prime of 2.01? I need to pick a number very close to 2.01. Let's say maybe 2.0101 minus y of 2.01. Divide that by 2.0101 minus 2.01. Minus here I need what's y of a number very close to 2, let's say 2.0001, minus y of 2 divided by 0.0001, or 2.0001 minus 2, and divide all that by 0.01. So I've got a difference quotient with difference quotients inside of it. So this is 2.0101 cubed minus 2.01 cubed over 0.0001 minus 2.0001 cubed minus 2 cubed over 0.0001. This is all over 0.01. There's some conversations to be had about the number of zeros here. I need way more than that, zeros here and here. Like, I need a really good, like a key thing I can't do is If my number very close to 2.01 was just 2, then I'll get the exact same thing here as I get here, and I'll always get 0. And that can't possibly be right. So I need these estimates to be a higher level of accuracy than this estimate of a quotient type of thing. It's just a nightmare. Anyway, you type all this mess in. What are we gonna get? Get your calculator. What is 2.0101 cubed minus 2.01 cubed? Now divide that by 0.0001, and I'm getting 12.120903. Is the first part of this. Okay, and now what is 2.0001 cubed minus 2 cubed? I can do is 8, and divide that by 0.0001, and this time I'm getting 12.0006. More zeros after that. Subtract these and divide by 0.01. So now I want... Okay, I've done a really bad thing, which is write down this number here. In general, you don't want to do this. But I don't remember how to get my calculator to put all this stuff in memory. 0903 minus, like, it's good that I've written down enough that I can see some digits where these things are different. So I am getting something somewhat meaningful here. Subtract 12.0006. Divide all of this by 0.01. I'm getting a number very close to 12. It looks like maybe the second derivative is 12. Oh, the first derivative is also 12. Why do I keep picking examples where the thing equals its own derivative? I suck at this. I'm the worst at example picking. That's a coincidence. Usually the second derivative is not the same as the first derivative. So that's how you would compute the second derivative, and by and large, I'm not going to ask you to compute the derivative, at least not using these difference quotients. The thing I do want you to be able to do, the thing that is more meaningful, is I want to be able to answer questions about f double prime is... So, like, the thing we know about the derivative, f prime is positive, means something. What does it mean when f prime is negative? That means something. I know that f prime is positive when f is increasing. I can look at a graph and say that the thing is increasing. Maybe I can look at a chart and say that the numbers are going up. That means the derivative should be positive here. F prime is negative when f is decreasing. I want to be able to say something similar about the second derivative. We're not going to do many computations with the second derivative, but we want to be able to make these qualitative type of description sentences. What does it mean when the second derivative is positive? Well, this is the derivative of something. This rule says if you are the derivative of something, you are positive when the something is increasing. So you want to tell me when f prime prime is positive, the thing you are the derivative of is f prime. You will be positive when f prime is increasing, and you will be negative when f prime is decreasing. Okay, I guess that's information, but what I really want to know is how does this connect to the original function f? This line is part of the thing, but it's sort of in a thought bubble because it's the less useful thing. What I want to do is, what does it look like when f prime is increasing? Well, there's two ways a thing can increase. You can increase by being negative and then getting less negative, or maybe then hitting 0, or you can be positive and then more positive. I want to think about if f prime looks like this, what does f look like? Well, at the start, f prime is very negative. That says that f prime is very negative, tells me that f is decreasing very steeply. And now it's decreasing, but less steeply. And now it's decreasing, but less steeply. And then it's flat. And then it's increasing, but a little bit. And then increasing more, and then increasing more, and then increasing more. This is what it looks like for f prime to be increasing. Either it was steep negative getting less negative, or it was shallow positive getting steep positive. Or both. Like, all of this could be combined. How do I give a name to this? I don't know if you use these words in an algebra class you took, but a shape of this curvature is called concave up. And if I did it the other way, I would be steep increase, flatter increase, flatter increase, flat, small decrease, steeper decrease, steep decrease. That would be f of x is concave down. This is the main thing to know about the second derivative. The first derivative tells me when the function is increasing or decreasing. The second derivative tells me if something is concave up or concave down. The technical definition of concave up, a graph is concave up when, if you connect 2 points with a line, that line segment is above the curve. If I think about grabbing any 2 dots of this curve and connecting them, you can still see the sky, right? If you're concave down, then the connecting points are all below the curve. You draw enough of these points, it always looks like a spider web. So this is a spider who can see the sky. A concave down spider is sheltered from the rain, or something like that. I don't know. That's not a very good mnemonic device. Luckily, the world has given us the best mnemonic device. This guy is concave up, because f double prime is positive. The words up and positive all come immediately to mind if you put eyes above the curve. The smiley face is up and positive, and the frowny face is concave down, because f double prime is negative. It's really easy to jump to some wrong conclusions about, well, if you're increasing, then you must be concave down, or if you're decreasing, you must be concave up or something. And those conclusions are not right. The increasing and decreasing are independent of concave up and concave down, meaning any of them can exist. Concave up is the smiley, concave down is the frowny. Increasing is going up left to right, decreasing is going down left to right. And the smiley and frowny each have an increasing part and a decreasing part. You can be increasing and concave up, that's the increasing half of a smiley. You can be decreasing and concave up, that's the decreasing half of a smiley. You can be increasing and concave down, you can be decreasing and concave down. Most functions can be split into chunks that are like this. And I drew this on the wrong side. Can you be neither increasing nor decreasing? The only way you can do that is if you are completely horizontal. Can you be neither concave up nor concave down? That would be a straight line. Like the concavity is which direction are you bending this board. If you don't bend it at all, that's the place when you are not. Yeah. Or I can think about it as if you are neither concave up nor concave down, that means the thing you are the derivative of, f prime, must be flat. So whatever steepness you are at is the same steepness constantly. That makes a straight line. That's what makes a straight line straight, is that its slope stays the same as you move around on the line. Always the same slope means horizontal, means, yeah. Um, all right, that's the end of 2.3. I have some announcement stuff I want to say, but I'm trying to be smarter about making videos that are usable. If coronavirus lasts 10 years, I want this to be usable for my next 122, so I'll wait and talk about that elsewhere. I'm going to stop streaming now. That's the end of 2.3. You should have everything you need to do homework 2.1 through 2.3.